No, hi guys. We've met already. We've been going through the course together for the past 3 days. So today we're going to talk about the synthetic control method. It's a relatively new method. It came out, I think, 2007, if I'm not mistaken. The whole purpose of the method is to allow us to evaluate policies that take place at a place in time, and then we can see the policy effect from that place in time going forward. So if we have a time series of data before the policy happens and after the policy happens, we can uh, find the impact of the policy. So usually it's very hard to find the impact of policies. You need a control group. So in this case, you don't need to have a control group because you can make a synthetic control group with other countries that might be similar to your treated country. So that's the whole idea. Um, yeah, here's the paper. That's the seminal paper by Abadi et al. In 2007 using synthetic controls, feasibility data, and it's a good paper to read if you guys need any feedback. If you need any information with regards to how it works, what data is the best, what are the limitations of the method, and what are the benefits of using the method. And here's another good book that Prof Steve Koch gave to me, and it helped me out. It's a causal inference book, and it has a chapter on synthetic controls, I think. So, oh, if you want to take a picture, yes. Oh, yes. Yeah, after that, no, it's cool. Yeah. So yeah, the synthetic control method allows us to estimate the effect of an intervention at an aggregate level, affecting one of the units compared to a donor group. So if you have a country, a province, a district, or a region of some sort, and the data of that region or country or province is aggregated, you can estimate the effect of a certain policy on that region or province or state or something, depending on what you're looking at. And the whole idea is that you have a group of donor countries. So donor countries is countries that might be similar to that country that you're going to use to form a fake control group so that you can compare that to the country that has been treated with the policy. Then you'll find the treatment effect, and we'll be able to visualize it and then also get the actual number for that treatment effect. So what's great about the method is that in macro, if you're trying to evaluate the effect of policies, it's hard to find a control group. Uh, so because no perfect counterfactual exists. For example, think about load shedding. If you wanted to see the impact of load shedding, you'd need to see South Africa before before the load shedding happened and after, but also South Africa if the load shedding didn't happen. But it's impossible to see South Africa without load shedding happening because it already happened. So how do you make a fake South Africa where the load shedding never happened to compare it to the South Africa where load shedding happened? So that's the whole trick. It allows us to create a fake South Africa where load shedding, for example, never happened. And then we use a set of countries to do that. And yeah, so as you know, we're trying to evaluate a certain intervention that was implemented on a certain unit, one unit, a single unit, using data that we collected, aggregate data, maybe GDP or any of the data you guys are used to. And the synthetic control is constructed using a weighting system, a weighted average of the different donor countries, the other countries that we use to form a fake country. So we'll weight them depending on which ones are most similar to the treated unit. And then those weights we'll use to make our new synthetic unit for comparison. So yeah, I think we've spoken about the logic, and yeah, another cool part is that it avoids extrapolation. In cases where this didn't exist, you'd have to, in my mind, if I imagine, you'd have to try to either um, extrapolate your way into a situation where South Africa didn't have load shedding, for example. And extrapolation, it's not that plausible in other cases. So here, you can be able to create a fake version of the treated unit and see its performance over many years as it tracks South Africa's performance in the key variable that you're looking at until the policy starts, and then you'll see a split. So you're able to check if it fits it well beforehand. So that's a cool part. Yeah, so the paper we're looking at today is a paper by Abadi, Diamond, and Mueller. It looks at the effect of tobacco policy in California, in the US. And what they do is the policy was supposed to basically demotivate tobacco consumption or sales in the state of California in 1988. There was a series of these policies implemented, but California had a strong policy to try and stop sales of tobacco. Proposition 99, it's called. So you'll be seeing Proposition 99 going forward in other graphs as well. So I took this from the paper itself, Abadi et al. So the black line shows California. As you can see, from 1970 until the time where the policy started, it's quite, it oscillates around zero, nothing happened until the policy took place. And all the other gray lines are actually the other countries the other states that they used to form a synthetic version of California to try and have the treatment effect, to find the treatment effect. So all of these gray lines are basically combined using specific weights that we'll try to calculate, not ourselves, through an optimization problem, and then find the optimal weights that help us take the gray lines that meet the criteria that will help us compare that synthetic version to California, and then we can have a treatment. So after you subtract the synthetic version of California to California, you'll have you can see the treatment, it's zero before the policy takes place, and you can see it goes up to negative 30%. So in this case, the policy had an effect at 30% negative, a decrease of 30% on cigarette sales after it was implemented. So yeah, that's what we're hoping to see. So here's a synthetic version of the gray lines when they are all combined using the optimal weights. You find a line like this. As you can see, they move together over time until they get to the point where the policy starts, and then you see a divergence. Yeah.
The slide. So those are countries. You apply some
States, yeah. Yeah.
States. States.
No worries.
You put some weight into. But I'm trying to get to say, to think those countries can really be a comparison of California. States can do the comparison
Of California.
Or you say just because like the US as well. So
Yes. So you'd go through a process of finding the perfect states that might be ideal comparisons to California to start with. They are just like you would in a normal regression, looking at any other impact or something. You'd look for countries that are similar to the country you're So you look for the literature will look for structural similarities in the countries. Are the economies similar? If it's countries, if it's states, are they the close proximity to one another? Are they part of a certain maybe common monetary area, something along those lines? And then it tells you that these are close enough to compare.
So it's not something like a physical model that's make us to agree that it's not something that you put in a model and then you'll give us something which could use just literature only.
Yeah, for the most part, it's literature. When you present your final paper and you try to state your case why those countries are the right countries, you'll get feedback from the crowd whether your case actually makes sense for the countries you selected. Of course, if I was trying to look at this policy, I wouldn't go to maybe provinces in South Africa to compare with the state, because structurally there's so many differences. So you want to get as close as possible. But yeah, it's up to you. Yeah.
Just in the past, especially in African countries mainly, you find that if one data for any African country without control, it's recognized by France and you then move to France. But then because we live here, we know that France is not really the same as any African country, and then doing some government policy. This was one of my idea, thinking if you're putting it like that, it might not really work, but if you were saying it, I understand. Thanks.
Yeah, so, yeah.
Yeah, so like I want to understand as well, like, so the period that, for example, let's say before the policy implementation and after the policy has been implemented, should that be the same, like, the period?
Length. Not necessarily. It depends on how much data you have. As you can imagine, I can imagine a case where you have 2 years before the treatment and 10 years before the treatment. When you run the optimization problem that tries to find the optimal weights, it would be much more accurate, I can imagine, with 10 years, if it's trained on 10 years worth of data than 2 years worth of data. So that after the policy hits, you can be confident that your weights are the countries will be the same much more if you use weights based on 10-year, pre-treatment and 2-year pre-treatment. So it depends, but I think the data actually matters. The longer the pre-treatment, the better. It sort of has to train the model to find, so the more the data, the better.
So there's also a limit, right? You don't want to start comparing countries 20 years before, because they're likely to be wildly different. So there is a trade-off that you make, like in anything. You've got to have enough data to believe in what you've got. You can have so much data that is struggling to not believe in it.
Oh, yeah.
So it's a practical.
Yeah, because I didn't want to jump the gun. Because that was actually one of the first few questions that I had when you were introducing
So how far back we go?
not necessarily how far back, but would there be an ideal duration for a study of this kind of synthetic?
I think it depends. For me, if let's say I'm looking at South Africa, I wouldn't want to go before 94 because a lot of changes happened, or especially massive political transitions, or structural changes in the economy, massive policies. There's a lot of changes taking place. I would want to keep it within a range that I have enough data, but not enough to make it hard to find states to compare to, So, but I don't know. It depends. Yeah.
Because I was just thinking, it does become a bit challenging to find periods, like long periods of stability or relative stability, you can put it that way. And then I thought maybe if you use maybe like you were saying, 2 years, maybe 2 years before, 2 years after, would that be a problem if you used data for a 2-year period, as opposed, because I would think it would be very difficult to get periods where there's...
I see what you mean. Ideally, what I'd do if I have an unstable country, I'd look for other unstable countries. You know what I mean? Like, then they're similar at least, in instability levels. Then I'm comparing apples to apples. If I have a very stable country, I'd look for other stable countries to sort something like that. And if I have a country that's plagued with war and a lot of challenges and a lot of structural changes, then I'd look for maybe other countries that are also having similar challenges. At least when I create the synthetic control, it would structurally underneath there would both be unstable countries. So I think it depends on the context, and it looking similarities as close as possible, so that
what I want to find out is it fine if I understand it to say like I can always use literature that is there in order for me to select this number of countries that are close to what I'm trying to achieve? Is it okay if I understand it like that?
Yeah, I think it's okay. Even the literature chooses different countries based on different reasons. I think it's all about stating your case why. If it's plausible enough, then I think it will work.
Maybe so one last comment, right? So a lot of these questions are what's the right answer questions, right? And if you ever think you've got the right answer, you need to quit your job right now. Okay?
Yeah.
So one of the things that people really try to do is they say, okay, well maybe I've got 20 years of data. I think that only 5 or 6 makes sense. So I run my analysis on that. And then I say, well, what happens if I add a couple more years? Does it completely just fall apart, right? And then you can say, all right, well, I've got this story for why this is an appropriate set of years to use. And now what happens is I've got some extra data, I take it a step further, and now everything falls apart, right? I think it falls apart because of this. So you've got this sort of complete, we call it sensitivity analysis, but it's also, it's hard work, right? You have to convince people that you've done the best you plausibly can in the circumstances you've got, right? And either they'll like it or they won't. It's the other part of our job, right? Sometimes they hate it, doesn't matter. This is really a case where there isn't a right answer, in my opinion. Right? It's about really convincing people that you've thought hard about this, that you've got a plausible set of guidelines for why these things should be together the way they're together, and that you play with it a bit afterwards to say, well, okay, it seems to hold up if you do a little bit different. Right? We wouldn't expect it to hold up if you change everything massively. Right?
I think that's a very good point, Prof. I think, and that's what we kind of do today, is kind of changing up some of the data, cutting the countries in half, trying to see how sensitive are the estimates, or how sensitive is the fit before the treatment happens to changes in variables, data. So it depends. It honestly depends. So, but yeah, in the previous graph, as you can see, this is a synthetic version of California, and California itself. These are this is per capita cigarette sales. So this is the outcome variable. If you subtract the one from the other, you should be able to get the effect itself. So that's where the first line in the first graph came from. It's after you create the control, the synthetic control. So yeah, there's key things that matter for us that we need, like almost like ingredients for us. We need to get this done. We need a treated unit, a country that got the policy itself that other countries didn't get, and then we need multiple untreated units. So if I was looking at tobacco policies, I would try to remove any other countries that had similar tobacco policies, because then it would mess with the analysis. And we need time series data, and we need a pre-treatment period so that we can optimize for weights, for finding the right weights that match the synthetic control to the actual state. And then another thing we need, at the end, your treatment effect, you calculate it by subtracting the treated outcome from the synthetic outcome. So you can think about it in terms of variables. In this way, we need x1 would be the treated, the covariates of the treated unit, so the x variables in a normal regression. X0 would be the covariates of the not treated countries or states, in this case the donor units. Y1 would be the outcome of the treated unit, what you're looking at, in this case cigarette sales, and this one would be the outcome of the donor units, Y0. And then you have a pre-treatment period, T0, and a post-treatment period, T1. So yeah, the whole idea of this method is finding the right weights to combine all the donor countries such that we can match the synthetic version of this combination to the actual state, the state that we look at that got the treatment. So the whole idea is that X1 basically represents, as we said, the covariates of the country or unit that received the treatment. X0 is the covariates of the unit that didn't receive the treatment. You're trying to minimize the gap between these two so that they're as similar as possible. So that's why we have a minimization problem. And yeah, so that's the whole idea into that. We're trying to find the weights that minimize this objective function.
Sorry? I don't know if I got you from this one. I mean, kind of from the previous slide. No, don't go back, right? But then maybe let's say, is there a minimum number of countries that you need to have a synthetic unit, or for example, it depends on the literature?
That's a good question. I think that's what we'll see today. The more countries or donor units you have, the more opportunities you have to combine those donor countries in the perfect way to compare with your treated unit. So ideally, you want a lot of options. But of course, it depends. You do sensitivity analysis, like Prof would say, maybe choose 40 countries, then maybe choose 30, and then maybe choose 60. Go above board. At some point, it wouldn't matter anymore because the optimization problem will find the weights that are optimal anyway. So even if I have 50 or 60, if it thinks that combining, let's say, New York and another state is the perfect, it gives a 50-50 weight to those, and that's the optimal. I can add 10 more countries. I don't think it would make any difference, 10. So I think it might help in cases where you add countries that are similar to, or states that are similar to your treated state. But if we're just adding more states, I don't think, yeah. So, yeah, that's a good question. We actually have a sample of countries and of donor units, and then we're going to cut them in half, and then we'll see what that does later on. So yeah, you're trying to minimize the objective function with regards to the weights. So these we call them W star, and that's kind of the secret sauce, if you like, or what we're looking for actually is the optimal weights that create the perfect synthetic control. And yeah, so W star. Once we have the weights.
Yeah, can we just go back? So it's easy to look at equations and sort of not understand them, and so nobody's asking about it, but let me just sort of point out, right? So think about a two-dimensional space. How do you find the distance between 2 points? Maybe sort of the classic Cartesian distance form, right? You square take the distance, right? And add it up, square it, whatever. And then you divide it by the norms. So this is basically what's going on here. It looks a little bit like a regression formula, but it's essentially taking the distance between the points, right? The points are now multidimensional points across California and all these areas, right? And you're trying to calculate the distance, and that distance is moving as these distance moves by the underlying calculation of W. So the W changes how much of that distance counts. Right? So that's what you're trying to do. And of course, it's a simple matrix calculation, so if you do it quickly, you don't have to do it.
And yeah, on the slide you can see the distance between x0 and x1. I think this goes underneath, again, typical relation.
So x0 is the
coordinates.
So was really making an inverse and multiplied by the term, the left side term should not be inverse and to multiply it by the other one to get to that W star.
Okay, so I probably said this in a more confusing way than I should have, right? Imagine you're trying to fit a line between 3 points of data. Right? What is a regression formula do? Basically, you can do this in your head. You can say, here's 3 points, this is the best fit. You can mentally see it. But the matrix math is saying, all right, what we're trying to do is we're trying to calculate this vertical gap between the line that's supposed to be there, right? And that's giving us some slope coefficient, okay? Think of that slope coefficient as essentially this W, right? So what it does is it takes the covariance between the X and Y, right? And that's what you see on the right-hand side. It's basically the covariance between the the control, the potential donor pool, and the actual California. Right? So it's comparing the donor pool to California. Right? So it's looking for covariance, if you will, between those. I'm simplifying it a little bit. Right? And then you're dividing it by the variance of the donor. So you see, it's really a little refreshing.
Once you have those optimal weights, now you're ready to combine them with the donor countries that have weights to form the synthetic control. So as you can see, we multiply the weights with the outcome of each of the donor countries that matter. Okay, all of them. Some of them will have 0 weights in cases where they don't matter. And yeah, we'll have y hat, the estimated y outcome, the estimated synthetic control, y hat s. So that's our synthetic control, the estimated weights, and the actual observed data of the donor countries. And this is done for all t that is pre-treatment. You know. Yeah, so that might be T0 there. So yeah, once we have the estimated y, the synthetic control, then we can subtract the outcome of the observed treated unit. Then we have the treatment effect. Treatment effect. Yeah. So key things you want to kind of watch out for from the Abadi paper. The parallel trends assumption. So you just need to make sure that the trends in the pre-treatment phase for the donor pool and the treated unit are similar to some degree. They match, and that's what this method takes advantage of, is that pre-treatment period, trying to make sure that everything aligns. And then you want to make sure there's no interference or spillovers. So if a policy is being implemented in this state, you want to make sure that it doesn't, for example, jump the border to the next state. Like there's a lot of policies that are implemented in one place, but they can affect the other places. I don't know, maybe migration policies can affect here and there. So you want to kind of, this would be ideally called SUDVA, making sure that there's no connection between the treatment and the control. So stability, you want to make sure that the relationship is stable over time. And limitations, of course, it's sensitive to the covariates that you use, your independent variables, and that's motivated by literature. So you go into literature and then you find what variables matter for your outcome variable that are good determinants, and then you can use these to make your synthetic control. And then data requirements, it needs a long panel, but it doesn't. It's a bad word. It doesn't necessarily need a long panel. It works with short panels as well. That's another actually advantage of the method. So if you have a panel with a small n but large t, it's good. It can work because the weights can be calculated regardless. It just has to have the optimal weights that combine these n's into a perfect synthetic control. So donor pool quality, poor match, poor estimate. Yeah, so this is straightforward. Some people would say garbage in, garbage out. So you need countries that are kind of similar already to start with. I think you asked that question. That was a good question. Yeah. So then we're gonna try to replicate this paper. I couldn't find all of the data, but we made do with the data that we could find for this policy. So Abadi, Diamond, and Mueller have a paper. You can search it, you can find it, and you can check it out if you want. And they do just what we've been reading about at the top. So the historical context. So the US implemented this anti-tobacco laws in 1893, but Proposition 99 only came in 1988. The whole idea is that it increased taxes to fund public health programs. It's a very good program because it it taxes things that are bad for health to actually give back to improve the health of society. So it's actually a good program, and it had a big effect, as you saw actually at the beginning of the presentation, 40 to 30%. So yeah, the impact: local policies helped reduce smoking rates, seen through or proxied by cigarette sales. Yeah. So they observed J+1 regions, J being the states, and 1 was treated being California, and then the remaining were donor countries. And if you look, just like we saw, you have YN, and YN represents the outcome without the intervention for the donor countries, and then YI represents the outcome for the treated unit. So AI, like Prof said, AIT represents the treatment effect in this case. And there's dummy variable. If you were treated, it's a 1. If you're not treated, it's a 0. Such that if we have California, in theory, we should take the synthetic control that we made and adding the treatment effect with D being 1 should get us back to California. Yeah. So this is similar to the Angres book. Then they have the expectations formulas with the for if you're trying to look for impact. It's a similar equation to that. And yeah, so we sourced our data from Walker. I'll just say Walker. I don't know how to pronounce the other name. Walker has a data set. If you search the reference, you'll find the data on a state level from 1970 to the 2000s. So it started in 1989, so we just have to keep that in mind. So it's a 19 years pre-treatment, and from 1989 forward is the post-treatment that we have. So, but at least we have 19 years worth of training. I remember there was a question, how many years are optimal? We use 19, and yeah. Back to the model. So in this case, you want to imagine, so California so if we broke this apart, okay, so let me go back actually. There's an equation that kind of, okay. So this part, so the treatment effect is basically the treated unit California, the outcome of the treated unit minus the outcome of the synthetic control. It's the difference between cigarette sales and the synthetic control and California. Think about it as the synthetic control would be California if the policies didn't take place. So if we have California, if the policies didn't take place, and California, when the policies did take place, the gap should be the treatment effect. So if you keep that in mind, when we get here, that means if I take the synthetic version of California, the treatment didn't take place, and then I add the treatment, which is the treatment effect, I should get back to California right now. So right now as it's treated. So yeah, that's how you can think about it. And the dummy is 1, the d-day is 1 if you were treated and 0 if not. So if we're looking at, for example, the synthetic version of California, that would be 0, and then you just get the synthetic version of California. Yeah. So we have 19 years pre-treatment, and up till 1998 when the policy starts. And I explained you can get that data online. It has tax, federal and state taxes, and per capita cigarette consumption through sales, proxied by sales. So this is a picture of everything we kind of had in the model. We have California and then 38 US states. So that's the amount we use, 38 US states and then 19 years. And this is the data that we could find. Retail price of cigarettes, the per capita income, of the states, sorry, and the population of each of the states and the federal and state level taxes, and also gross cigarette revenue. And then our outcome variable is gross sales per capita of cigarettes. The per capita? Yeah, that's how they did it in the paper. They logged the per capita income. I'm not sure why in this case. Do you happen to know, bro? I'm not too sure. I can check if you want, but yeah, like, they logged per capita income. I don't think maybe I don't know. Maybe the range of the income variable was too different in different countries. I log it to try and make sure the range is not too much, but I'm not sure. Yeah. Yeah. But I don't think it matters too much. I don't know.
Well, it's surprisingly a long population.
Yeah.
Because you have massive differences. The difference in per capita income in California compared to most of the state, even back then, is quite a bit.
To try to squeeze.
Excuse me.
From a population perspective as well, California is bigger than most states by that stage as well.
That's quite interesting because it's already per capita, and then they squeezed some more. So, but yeah, and yeah, so this is the first try. No, sorry, this is not yet the first try. This is cigarette sales before implementing the method itself. So here you have the donor pool. So I took the mean of all the outcome variables in the donor pool, and then I took the actual per capita cigarette sales in California. And before we apply the method, you can see there's no match pre-treatment. The policy happened here, and they both go down. So you can't really tell where the treatment, what the effect was of the treatment. So,
How much did Matt talk about parallel trends?
he spoke about it today, but not much. So,
Okay, so the first rule of difference in difference is that you want what's going on in your control group to look like what's going on in the treatment group before the implementation of drug intervention, right? Yeah. And so if you ignore the first couple of years on that picture, I would be really happy with that. Right? They're parallel. Right? So they look very, very, very similar. They start to separate after the pause. So it does fit the underlying sort of DD story, which is that we want parallel trends. And that's actually a useful piece of information in this sort of analysis. It suggests that, okay, the donor pool isn't wildly out of line as a donor.
I think that's a very good point. I think that answers the question of whether how do you know you selected the right set of countries? So you can just get the mean of the outcome and then see do they go together over time. Now, thanks, Prof. That's good. So here's some summary stats for California. I mean, we already plotted per capita cigarette sales, this one. So we kind of want to see similarities, but there's going to be some differences, just like we spoke with the parallel trends. Some stats will be similar, but still differences that are there. So you can see the average per capita cigarette sales, similar, and then you have retail prices of cigarettes, similar. The log GDP per capita is also quite similar, although standard deviations are quite different, but at least the means are relatively similar. So
When, let's say, on the if you manage to draw the graph and then to get that this means so it's that you selected the right things or the set of means, and then will there be any way that you can be able to see that this country or a set of maybe not a country to say, but this unit, a particular unit in another unit that's dependent what they look doing? Will there be a way that you can be able to tell like this is one is not does not belong?
It's not good. Yeah, I think you'd have to open up the data, and then look which country maybe is too different from the other countries that you have, and then just look in the data. Here we have 38 countries. It wouldn't take too long, I can imagine. I would do something like this. And then I don't know.
That's an ex post statistical test.
Expose statistical test. Is it? It isn't. Okay, so that is a bad example because all of them are actually they're centered around 0. So something was done. It's not the actual data. But in this case, I would do.
Go back. So, I said it's so the black line is the California story, right? And so what they do to infer whether or not this is a statistically significant effect is they imagine that the policy happened in the other states. They apply the exact same method and they calculate how much consumption changed in that state. That's what you see with the light colored lines. In some cases, they went up. In some cases, it went down. But California is one of the lowest, almost always.
Mm-hmm.
So this is what they call it's a very specific type of p-value, and it's literal, right? So there's, for sake of argument, there's 50 states. California is the lowest, so the p-value is basically 0.02. Right? If California ended up like 10 out of 50, it would fly. But it wouldn't be statistically significant, it would be like 0.2.
So like you talk like you're saying those states with gray lines, right? That they are is after they put the policy on good things.
Yeah, so it's like a simulation concept or a thought process. It's like, okay, well, let's imagine what happened. We need a way to test the significance of this change in California because it's just one state, right? And so the idea is that, well, let's just pretend that this happened in the other states instead. Let's apply the same method. And let's figure out what their black line picture would be. Okay? But they're plotting it in gray in this picture. Right, so this is for all the other states, where the other states were treated as if they had the policy implemented that California. So right? California is always the lowest. But so their argument then is that because California is always the lowest, we can think of that as a statistically significant result. Right? If it was in the middle of all the states, you'd say, well, maybe not. The other states were bigger, and the other states didn't have any policy.
Post designation. Yeah.
Was a shock applied to this model?
No,
I don't-
it's a policy.
I'm pretty sure that's a discussion.
Now, the more the better. Let's go.
How much of just thinking in California cancer they put a discouraging the sale of cigarette. How much of people going to California and go buy cigarettes never encounters?
They removed some countries that were problematic. Yeah. So the paper actually discards any other country that might be problematic for those reasons, and then they keep the states that are less problematic. That we mentioned with the
So nobody doesn't really apply in practice, but it's technically illegal. Buy cigarettes in one state and transport them elsewhere because there's a tax label from that particular state. It's supposed to tax is supposed to be paid in that state. Certainly it happens. Right? So, I'm not trying to
I'm also sure it kind of still does somehow, you know.
If you've ever seen like the first Beverly Hills Cop, right? Eddie Murphy is actually trying to arrest the mob because the mob is just, this is what they made their money with, their cigarettes. And they would get them without tax levies, so they didn't pay the tax on them.
And move them out.
So they lost them. Anyway, so that trying to answer your question, it's, I don't know what the level of sort of legal trade is, but I think they removed Nevada and Oregon, which are California's only neighbors. That's nice. So it still doesn't stop them from going to.
Can go 2 states, yeah. Yeah.
Because what I would think you will see is an increase in sale in the different countries.
Yes.
And they might think if we didn't apply this will increase. But it's just this guys now what they are saying.
Yeah, it's possible. I think it's a plausible query or question to have. I would also remove neighboring states. Yeah.
Removed, I think it's the best point. Yeah.
Yeah. It's good. Oh yeah, so this is what I was sort of talking about. If you are trying to see if your donor countries match your treated unit, maybe you could make a graph like this with each of the countries and then see, do the trends go up and go down? Do they move along similar trends, you know, over time? Just so you can tell which one's a bit off and then you can cut them. Yeah. So, all right. So yeah, so here we have 2 controls. So now we're in testing how sensitive the model is. We have 2 controls: income, GDP per capita, log GDP per capita, and price. So you can see it's terrible. The trends don't match. They do still kind of match a bit, but they don't match much over time. And because this is not going to get, the match is very bad, the weights are not so good, you can tell that the treatment effect will also be a bit off. In the previous, I just want to go back and just show you what they got as a treatment effect. So they get minus 30%, 30% decrease basically in cigarette sales. And what we get, first time, it's over 60%. So now we know that it's sensitive to the variables or covariates you use in your model. You need to have more covariates if you need much more precise estimate. So 2 won't cut it. California is still below the line, so somehow it's still picking up something, but this is very bad. Then now we add population. It's gotten way better, and if we look at the effect, it's still not a precise match, but we add minus 20%. They got minus 30%. And since I don't have all that data, I'm going to push it as close as I could get, but I can't get to exactly where they got. But the effects are similar. I also get close to 30%. Then I added the federal taxes and revenues. Still not quite there. And the effect has moved just a bit lower than 20, I'd say. It does get a bit to 30, but not immediately as quick as the other graph does. So the more controls we have, the better the model. So it matters what your x variables are or your covariates. So you kind of need to look at the literature that we learn. You need to look at the literature, and then you figure out what determines your outcome variable before you can consider those variables as covariates for the model. So it still kind of works in the same way you would in a regression analysis or any other study where you're assessing impact. And then now I cut the countries in half from 38, and it doesn't seem to have a huge effect. If compared with the previous one, it seems like this gap here just got a bit bigger. But when you look at the treatment effect, it's off. It's completely off. So the amount of countries you have matters. If you have too little, then it's very hard for the model to find optimal weights. Even if it does, I guess, like it did here, the treatment effect will be a bit off. And then I cut to a quarter of the countries. It seems to improve a bit more. I don't know, maybe a stroke of luck. Yeah, but I think the general lesson is that we need a good number of countries and we need good determinants. Yeah.
So how do you select the countries?
The countries.
When do you reduce the number? Do you do random selection?
So what I did in this case, that's a good question. I tried the countries that got the weights the first time. I removed them from the sample to see whether it will search for new weights and whether this will make a big difference. So I tried to make it hard for the model to find it. So every time I cut in half, I cut countries that were given weights, yeah, to see how. Yeah, so because it calculates weights, I think it will always try to find a good combination of anything. So you won't completely be fully off, but you'll be a bit off. Yeah. And then, yeah, that's it. I can show you the weights if you want to see the tables of the weights for each of to see which countries seem to matter. So I just converted the presentation into a PDF and I have some of the weights. So here's when we had price. You see everything is a 0. This is 2% Maine. Kentucky is 80%. And Nebraska 10%. Cut them in half. Now it found new weights. 40%, 46% Vermont. And then South Dakota 54%. Then we cut again. No, this was actually not before that. This is when you add more covariates actually. So that's quite interesting. So it seems even when you add more covariates, it still looks for optimal weights in different countries. It doesn't stay with the same countries clearly, which is quite cool. So here it's stuck with Vermont and South Dakota, and now we cut the data set, and 99%, 90% at least, goes to Virginia. So cut some more, and then it gave North Dakota and Ohio 60 and 38%. So it always tries to find weights that work, but it depends on the covariate and I don't know, the time period I can imagine, and yeah.
So like after cutting those countries into two halves, the halves in the equal. Like after cutting them, you run for the other half and also for the other half.
So I run before the cut, and then I cut the data set, then I run again. Then I cut the data set, then I run again to see how the estimates change. Yeah. Yes.
This seems like a very new, exciting way of doing things.
Yeah.
And it's very similar to the CGE modeling.
To CGE modeling. Oh.
Not what's good.
It seems like
so.
CGE modeling comics.
I think Prof, you might.
CGE modeling is a series of equations that are built, right? And the equations have a series of parameters in them. And you then, once you have those parameters in place, you can alter something in the set of equations and it'll reach a new equilibrium, right? The only equation we have here is this weighting equation. This is literally one equation, right? And And so the only similarity between this and CGE is the idea that you will reach into equilibrium when you change the sim. But CGE is massive, but there's, you think Heinrich's model has like 150 equations, which is very big. Sorry, one more thing. The point you're making, I don't think you would sort of highlighted this probably enough. The initial analysis, despite having 38 states, picked 4, right?
Less than 5. Yeah.
So only 4 of the states were actually used, had positive weights. All the rest had 0 weights. And he was sort of saying this out loud, but he wasn't highlighting it. And he would cut the sample by the bottom 2 states, or whatever, right? So you have a big donor pool, but the method doesn't choose them all. Chooses almost none of them, in fact. Which maybe makes it harder to believe. You know, I think that's what I'm thinking about. But it's very. It doesn't sort of choose a little bit of this state, a little bit of that state, right? It chooses a bunch of a couple of states, a bunch of a couple of countries.
Yeah. Yeah, and I think you. No.
How can you relate this to the proposed scoring?
The weighting idea, I'll talk about that's exponential tomorrow, right? But this weight is sort of like propensity score weight. Right? So but in propensity score weighting, we sort of weight everybody. So that's the biggest difference. You might throw out a few because of loss of overlap, but this method actually throws out most. Here the weights sum to 1. There the weights are between 0 and 1 because it's a probability model. But they don't sum to 1.
And I guess you wouldn't at the end.
Conceptually, the idea is
It's similar, yeah.
A match, something that looks like a treaty person, a treaty state. But there's much less data. Like 38 states with a couple of covariates as opposed to a couple thousand observations cross-sectional. There's lots of control variables that you can use. This is like a weird macro panel density discriminant.
And yeah, like you said, it's fairly new. I think 07, that's when that paper, not so much I can imagine, but the body paper after that, they took off. Yeah, from what I can find, it seems. Yeah, if I'm mistaken.
I love it earlier, but there's probably yeah, it's still fairly new.
If there's no other questions, thank you for your time, and I appreciate this opportunity.